Now that we have our state information, we can proceed to calculate the qualities of interest for us. So let's do that. Okay, things I'd like to know are, number one, how much power can the system produce through work output of the two turbines? And also, what did I have to pay for to get it? How much heat transfer did I have to use in my steam generation for both the primary heating and then the reheating? And then with those two numbers, I can calculate the efficiency. So let's tackle the power output first. Okay. The work output, or the power output rather, of my cycle, I can apply the first law to in this case, I've got three things. I've got turbine 1, which is producing work output, turbine 2, which is producing work output, and then the pump, which is requiring work input. So I'm going to write this as the rate of work of turbine 1 plus the rate of work of turbine 2. And then just to make sure we're subtracting this number, I'm going to say minus the absolute value of the power needed to drive the turbine. Okay, I can replace those with the first law of thermodynamics for each of those systems using the appropriate assumptions. And note, I'm just writing m dot because the same mass flow rate is flowing through each leg in the system. So here's the power output of turbine 1. Here is the power output of turbine 2. And then here is the here's the power needed to drive the pump. I have to subtract that off. Okay, at this point, I don't really need to know the mass flow rate. I can divide, since it's the same mass flow rate everywhere. And I have the specific work of the cycle is equal to H1 minus H2 plus H3 minus H4 minus H6 minus H5. And plugging in the numbers, I get 1,390 kilojoules per kilogram. Okay, so that's the specific work I can get out of my power plant. Now what I have to pay for, that's going to be the total amount of heat transfer coming in. And we have to keep track of the two separate loops here. So that's going to look like mass flow rate times H1 minus H6. Okay, that's the rate of heat transfer to the fluid as it exits the pump and is heated before it enters the turbine. And then the reheat is going to look like the mass flow rate times H3 minus H2. And it's the same mass flow rate, so I can divide both sides and get this in terms of specific heat transfer. And I can plug in my enthalpy values and find that the total amount of heat transfer to my working fluid is 3,800 odd kilojoules per kilogram. Okay, and with this now we can calculate the efficiency of my cycle, the thermal efficiency of my cycle, again defined as what do you want divided by what you have to pay for to get it. And that comes out to about 0.364 or 36% thermal efficiency. Let's delve further into the model and look at some trade-off studies to better understand what's going on here. You can download a fluid prop file from the course website. I'm going to scroll down here. You can see I've got textbook problem. I think this is 830 actually, since it incorporates the isentropic efficiencies of the pump and turbine. And in this example, I'm going to explore the effect of intermediate turbine pressure. Okay, this is built the same way as the previous spreadsheet that I introduced in the last class. My fixed parameters are up here. My turbine pressure 100 bar, my condenser pressure 0.06 bar, and the problem gives the isentropic efficiencies of the turbine and the pump. I'm going to keep the superheat of the first turbine at 480 Celsius, and then also the temperature of the reheat into the second turbine, I'm going to also keep it 480 Celsius. What I'm going to vary is the intermediate pressure. The intermediate pressure right here. Who says it has to be 7 bar? So I'm going to vary that, in this case, from 1 bar up to 100 bar, and look at the performance of my cycle. And again, this moves left to right, and it follows essentially each standard calculation you make as you have to work your way through the cycle. Here's the work output of the cycle, the specific work. Here's the efficiency of the cycle. Okay, if I'm looking to maximize the work output, it would appear the second value for intermediate pressure of 2 bar is getting me the most bang for my buck, so to speak. The efficiency, if that's what I'm trying to maximize, then let's see here. It would appear about 20 bar is my best intermediate pressure under which to operate. On the next page, I have the effect of turbine number 2 exit temperature. So if I scroll back up here, we said state 3 was at the same temperature as state 1. It could be anything below in this case. So note that we fix the inlet temperature to the first turbine at 480 Celsius. In this case, I'm fixing the intermediate pressure at 7 bar, and then I'm varying the reheat of the second turbine from 170 up to 500 Celsius. And then let's see again how that affects our performance. The efficiency appears to increase. The work output increases as well. So I would like to drive that reheated turbine as far into the superheat region as possible. Now tables are fine. Sometimes charts give us better overall understanding of what's happening. So I'm providing 3 figures here that explain those 3 things we just looked at. The first one here, I've got the turbine 2 pressure, which is what I'm varying, the intermediate pressure. And I've chosen the superheat of 480 Celsius, and I want to see how that affects the cycle efficiency. And you can clearly see there's a maximum, and it's around 20 bar for the intermediate turbine pressure. I also fixed the intermediate pressure, and I varied the turbine 2 exit temperature to see what that did to the cycle efficiency. In this case, we see I just want to drive that turbine 2 exit temperature as high as I possibly can. So the last image here incorporates the best of both. I'm going to keep that 20 bar intermediate pressure, and I'm going to vary the turbine 2 exit temperature, and I can see I can get my cycle efficiency as high as about, what is that, about 0.37, so about 37%. So in your projects, you're going to have to consider a lot of different levers, so to speak, that you can manipulate to improve the performance of your cycle. We want to produce the greatest amount of work output, and we also have to stay within the realms of reality as we know it, in terms of what pressures are valid, what temperatures are valid, and then also new information we've been learning, such as turbine quality being 90% or greater at the exit.